Now that we've taken a look at the formation of an action potential and how we send that action potential down through the neuron to the ends of the axons to get to the next cell, we can now take a look at how we can speed that process up and utilize myelination to help us out with that process, and then how we get to the point of actually having action potential in the first place through the use of graded potentials. And so when that neuron is sending its signal, we have a way of changing how we're going to actually have that speed occur. One of which is through the use of myelination via saltatory conduction. And so we're going to actually allow for our signal, in a sense, to jump and skip a large portion of the actual axon. Versus with continuous conduction, we've got to depolarize and cause an electrical change along the entire length of that axon. And so that whole axon has to actually depolarize in order to get us to the end where we can then send the signal on to the next cell. So if we look at kind of these two neurons here and look at what's going on, the same amount of time is passing by, but as we go from 1 millisecond, essentially the process is even. And so between continuous conduction and saltatory conduction, we've got the same amount of distance covered in that first segment of time. By 5 milliseconds, though, we can see that for the movement of our action potential, we've now jumped ahead a little bit in our second situation where we've got a saltatory conduction because we have those myelinated axons there. By 10 milliseconds, we can see that the saltatory conduction, we're almost to the end of that neuron, versus continuous conduction, we're still way back at the beginning. And so the speed of that conduction is immensely increasing when we use a myelinated fiber. And so with that, we're able to, once again, skip from one node to the next node to the next node and allow for that speed to increase very, very fast. We only have to actually depolarize in those particular regions that are there. And so when we look at the two kinds of cells, and so when we have a nerve here, and we're looking at the axons themselves, and so the purple portion is the actual axon, and the darker, almost maroon portion here is the actual myelin sheath. So that's the insulation that's there. It's no different than if we had insulation, in a sense, on a wire. If we have insulation on a wire, it allows for that electricity to move through the wire without any ease. It's not going to have any problems as far as jumping to something else, and it's going to move very, very quickly. The more insulation we have, the less loss we have along the way. And in these unmyelinated fibers here, they still have a Schwann cell that surrounds them, but it doesn't completely wrap itself around the outside of the cell. Excuse me. So we're lacking that control of loss of electricity, in a sense, along the way of those axons. Versus with the myelinated fiber, we can see it's fairly heavily myelinated here. The Schwann cells themselves are individually surrounding each one of those axons. The growth of the myelin sheath, when it comes to the central nervous system and the peripheral nervous system, this is accomplished in two different ways. In the peripheral nervous system, this is accomplished via Schwann cells. And so Schwann cells are what we're going to utilize in order to make this happen in the peripheral nervous system, which also means that the axon, as it's traveling along, is going to have multiple Schwann cells. And so we're going to have many, many Schwann cells along the entire length. And so each individual Schwann cell is going to create its myelin sheath as it wraps itself around. And in the beginning, it almost kind of looks like a hot dog in a bun. And so the axon itself is our hot dog, and then the bun is the Schwann cell. But in this case, that Schwann cell just keeps on growing. And as it does so, it's wrapping itself around the axon. And it continues to wrap itself around and wrap itself around. And one of the things you'll notice is that as it does so, it's squeezing out all of the cytoplasm. All the cytoplasm of that Schwann cell is leaving the outermost portion here, which is still cell membrane, which is made up of our phospholipid bilayer. So we've still got a plasma membrane there, and the lipids and the phospholipids and everything that's inside there creates a great amount of insulating properties to that axon that we have. And so that's going to allow us to create this process in and around the cells. But this is happening in cell after cell after cell after cell as that axon continues to grow. In the central nervous system, we're going to use oligodendrocytes. And so the oligodendrocytes we find only in the central nervous system. These ones work in a slightly different way. And so in the oligodendrocyte, that one oligodendrocyte is going to potentially attach to multiple axons. The other big difference there is that the space in between the nodes, so in between these nodes of Ranvier, is much greater. And so with the axons on a Schwann cell, we would have, in a sense, a Schwann cell here, and then a Schwann cell here, and a Schwann cell here, and a Schwann cell here. So we've got many Schwann cells, whereas in this case, we only have a single oligodendrocyte. And that oligodendrocyte is able to create that wrapping around more than one axon. So it's able to surround them in more than one place once they're there. And so each one is going to have that similar process. We find it in different areas. The end result is that we still get a myelinated fiber. And in this case, it's going to be even faster because our spaces in between the nodes is much greater. The other advantage of having a myelinated fiber is that we can concentrate all of our channels, all of our protein channels, in just those little nodes. And so the node itself is the only area of the neuron where we have exposure to extracellular fluid. And so all the rest of this space here, it does not come in contact with any extracellular fluid. So all of the sodium and potassium that's anywhere within the cells, I'll make some more potassium here since we're going to have more on the inside, and we're going to have more sodiums on the outside here. Each one of those is able to then go through those particular channels. And so when we have our voltage on the inside go from being negative to all of a sudden becoming positive, that's going to open up these voltage gated channels, and now sodium is going to be able to rush into the inside of the cell, potassium is going to be able to rush outside of the cell, and we're going to quickly be able to depolarize that cell. But again, this is only going to happen in this node. This only happens at the node of Ranvier, and so that's the only place where we have to go. So this allows us to jump from one node to the next node, and then this one coming in over here jumps to this spot, and that's the only place where we actually have to depolarize the cell at that point. So the myelin sheath, again, allows us to skip all those little pieces. And so essentially the only place where we're going to have this process occur is in those nodes. The internode area does not depolarize, and so it doesn't have to change its voltage inside there. And so we're going to very quickly, as we begin our action potential, and so in the initial segment here, we're going to get to threshold, and then we're going to bring that voltage up to a positive 30 millivolts. That positive 30 millivolts has brought all of that sodium into the inside of the cell, and now we have a local electrical potential that moves over to our next node, and at the next node it starts to bring us down to threshold. And so now we start to get down to threshold. Those voltage gated channels open up. Again, sodium starts to rush into the inside of the cell. That depolarizes this particular segment at that time. And those sodium ions are going to, in a sense, move toward the next segment. And they're going to make that movement over to the next portion there. And then the next one is going to start to depolarize. And we keep on going from there on down, all the way until the end of the axon at those axon terminals that are there. Once that voltage has gone past, remember that this is going to then repolarize. And so we're going to go back through the process, and we're going to come back to a negative 70 millivolts here, negative 70 millivolts over here. And so it's going to repolarize. It's going to get us back to our normal resting membrane potential. And then another action potential can come along once again. So the action potential is, in a sense, the end result. That's what we're trying to get to. But in order to get there, we oftentimes have what we call graded potentials. Graded potentials are kind of like almost like a false start in a sense. And so the stimulus to our postsynaptic neuron is not quite great enough in order to get us an action potential. And so if we're sitting here at negative 70 millivolts on our neuron here, and we've got to get up to negative 60 for our threshold, these graded potentials can get us, in a sense, anywhere in between that negative 70 and then negative 60. Anywhere in between there, and nothing happens. It's not until we hit that threshold point where we then can have our action potential occurring. And so both of these neurons could be firing off and firing off and firing off, and they're still not getting us to our threshold. That means that the action potential is not going to happen. The graded potential itself is, to a certain degree, kind of like also throwing a stone into a pond. When it does so, it then creates concentric waves, and those waves go out. The further away that those waves go, the weaker they become, the smaller they become until it eventually dies out. And so that's kind of like what a graded potential is. It's like we threw a little stone into the pond, it created some waves, and then they eventually disperse. They don't actually get back all the way to us for those. The action potential would get the wave all the way back to us. So any given axon and any given neuron can have a multitude of neurons that are being excited onto another neuron that's there. And so all of these connections here that are happening on this cell can all be firing off at the same time. So a single neuron may receive information from thousands of different synapses. Some of them are going to be excitatory, some of them are going to be inhibitory. And so we're going to have two different possibilities to those. And if all of it, when it adds up, eventually only adds up to a process where we don't get to our threshold. So if threshold is not found, then there's no action potential. So there may not be enough of the positive side, the excitation, in order to get us to the action potential itself. We've got to get up to that point. Otherwise, nothing happens. It's all or nothing. And so we have either get it or we don't. But what can happen is we can start to get multiple of those coming in a couple of different ways. And so we can summate either through temporal summation or through spatial summation. Temporal summation and spatial summation are similar to one another, just kind of who's doing the stimulating kind of changes a little bit. And so with temporal stimulation, we can have a single neuron here stimulating our cell, and as it stimulates, it's going to cause a little bit of a blip in the voltage. And so we get a process where that voltage has changed. And so down here we're at negative 70 millivolts, and it brought us up to, say, negative 65. But then if another action potential comes sufficiently soon, that next action potential may get us to our threshold, and then it shoots off and it skyrockets from there, and we get an actual action potential. So if there's enough and more frequent enough action potentials, so if the action potentials are coming often enough, that can get us to an actual action potential. The more frequent they are coming, essentially the stronger the stimulus it is on this postsynaptic neuron. Similarly, when we have spatial summation, now we've got multiple synapses, and they're all firing off at the same time. So they're all doing their action potentials at exactly the same time. So they are taking us again from that negative 70, and all at the same time, they bring us up to potentially our threshold. And so the more synapses that are firing all at one time, if we've got hundreds and hundreds of excitatory types of synapses, all of them leads to a stronger stimulus. If we've got less synapses, we get a weaker, rather than a stronger, we get a weaker stimulus, and that weaker stimulus then leads to just an action or just a graded potential. We don't get a action potential at that point. And so we need to get to the point to where we have a strong enough number of action potentials or a more frequent enough action potentials or graded potentials to get us to that action potential point, to get us over the edge, to get us to the action potential that we want at that point in time.